Hello everyone, I'm Keisuke Tsugira from Keio University. I'm going to present P3Net, PointNet-based Path Planning on FPGA. Path planning is a key component for autonomous mobile robots and comes with many useful applications. It tries to plan a collision-free and shortest possible path. Path planning has been extensively studied for decades, but it currently faces two challenges. The current approaches have high computational cost to obtain high-quality results and comes with many weaknesses. In addition to that, path planning is usually executed on mobile robots with limited resource and power supply. So to counteract these challenges, in this work, we devised a lightweight deep learning-based method and implement it onto FPGA SoCs. Sampling-based methods are the current mainstream. Starting from RRT, many variants have been proposed to improve efficiency and convergence speed. Sampling-based methods are appealing due to their simplicity, but they also have weaknesses. There is a trade-off between the computational effort and the quality of the solution. The construction of a random tree like this is a sequential process, so it is not easy to accelerate such methods. Deep learning-based methods are the current research trend. In this work, we focus on MPNet, which has some strong benefits. It is a general and flexible framework and can be applied to a wide range of planning tasks. It uses simple neural networks, so it is very easy to implement and more suitable for hardware acceleration. Importantly, it usually requires less computations than the sampling-based methods. Our contribution is twofold. First, we improve the parameter efficiency and stability of MPNet and propose P3Net. We then create an FPGA accelerator to improve the speed. So this is the first work for the learning-based path planning targeting FPGAs. MPNet uses two deep networks, encoding network, ENet, and planning network, PNet. We first use an encoding network, ENet, to encode environment information into a feature vector. We then use PNet multiple times to compute waypoint notations in the path. We are going to improve these two networks and accelerate the network inference on FPGA to improve the entire performance. First, we look at the encoding network. The original network has three weaknesses. It doesn't have permutation invariance. So if we swap points, we get different feature vector. So this is not robust. In addition, the number of input points is fixed, and the number of network parameters depends on the number of inputs. So we use PointNet as a backbone of the encoding network, as shown in the right figure. In this case, we first compute pointwise features from the input points and aggregate them using a max pooling operation to get a feature vector. It comes with a number of benefits. It accepts point clouds of any size, and it has permutation invariance. The number of parameters are also reduced by more than 30 times in the 2D case. The number of feature dimensions increases by 9 times. So feature vector contains more detailed information about the environment. PointNet-based encoding is very easy to implement on FPGAs. We pipeline the feature extraction as shown in the right figure. We also parallelize the computation inside each layer by unloading loops. Note that the buffer size and the number of parameters are independent from the number of points, so it achieves the scalability to some extent. Next, we look at the planning network, or PNet. In experiments, we found that the original network shows a low parameter efficiency, especially in the 2D case. So we shrink the size of the planning network by reducing the number of building blocks. We hope that PointNet-based encoder produces useful features which better capture the environment. So we expect that the shallow planning network is sufficient for the planning tasks. In the 2D case, the number of parameters is reduced by more than 30 times. By combining the improvements from encoding and planning networks, we reduce the number of parameters by 32 and 5.4 times in the 2D and 3D cases, respectively. The planning network is also very easy to implement on FPGAs. We parallelize the computation inside each layer, and we implement the dropout layers by generating pseudo-random numbers using LFSR. So we propose P3Net as a combination of the PointNet-based encoder and the shrunken planning network. We show the board-level implementation for the Xilinx ZCU104 evaluation board in the right figure. 2 deep networks are packaged in a custom IP core, which is written using HMS. We made 2 designs for 2D and 3D path planning tasks. Importantly, the network parameters are stored into on-chip memory to reduce latency. This is possible thanks to the reduced number of parameters. We describe the baselines and datasets used in this work. As a baseline, we used MPNet and 3 sampling-based methods, namely RRT star, informed RRT star, and BIT star. We used 2 datasets, simple 2D and complex 3D, which are provided by the MPNet authors. These datasets contain a set of environments, point clouds representing the environment, and optimal paths. We first evaluate the planning success rates in the 2D case. Our proposed P3Net generalizes well to the unseen environment settings. Notably, P3Net achieves 22% higher success rate than vanilla MPNet with 32 times fewer parameters. And P3Net outperforms RRT star and informed RRT star and is comparable to BIT star, which is one of the state-of-the-art sampling-based methods. We can also see that FPGA implementation gives higher success rate, so the performance is not affected by the use of fixed point numbers and simple pseudo-random generators. We then look at the execution time and speedup in the 3D case. FPGA-based P3Net is the fastest and plans a path in sub-seconds. It is 56 times faster than RRT star, 4 times faster than BIT star, 9 times faster than MPNet, and 7.7 times faster the CPU-based P3Net. We compute the cost of the estimated path, which is defined as a ratio with the length of the output path to the length of the optimal path. The average path cost for the P3Net is closer to 1.0, so P3Net can produce near optimal paths like other sampling-based methods. And FPGA implementation gives similar results, so we maintain the same quality of the output. We finally evaluate the FPGA resource utilization and power consumption. Our design consumes a large part of on-chip memory, since we store neural network parameters on block RAM and ultra RAM chips to reduce the latency. DSP blocks are mainly from matrix operations in free connected layers. Now, since the utilization for LET is low, we could also implement other parts like collision checking. The right table compares the power consumption and energy efficiency. In the 2D case, the entire consumption increases by around 50%, but the energy efficiency is improved by 4 times, thanks to the 6 times speed up. And we visualize the outputs from P3Net and the baseline methods. The red and blue lines are the results from P3Net. And we can see that P3Net can successfully plan a path even in difficult settings. So we summarize the contents. We present the first work for efficient learning-based path planning on FPGA. Compared to MPNet, our proposed P3Net offers 22% higher success rate with 32 times fewer parameters, and 6 times speed up, and 4 times better energy efficiency in 2D case. And it generalizes well to new environments, and it is comparable to state-of-the-art sampling-based methods. Future works include the comparison with other learning-based methods, evaluation under difficult environments, and improvements for the complex problem settings. Thank you.